Young. I'm the director of the Massachusetts Space Grants Consortium, and this is one of our enjoyable events that occurs annually to invite a distinguished lecturer to come up here to Cambridge and to talk about an aspect of space research. There are many other activities of the Massachusetts Space Grant Consortium. I urge you to keep up with us by consulting the website, MASGC, which is listed on the back of the program for today's events. All of these events are open to the public, and you're welcome to participate. We are also the hosts to a spring seminar course, Modern Space Science and Engineering, which meets every Wednesday at 3 o'clock, and those lectures are also open to the public, and the schedule is on that same website. And incidentally, for those students here who are registered in the course, would you at 4:30 congregate up where Professor Hoffman and I are sitting now, and we will go over some course business. With that, I would, as well as take attendance. With that, I would like to turn over for the introduction of today's distinguished speaker, the co-director, turn this over to the co-director of Massachusetts Space Grant, Professor Jeffrey Hoffman, who had hands-on experience in space with one of Professor Giacconi's key contributions. Jeff?
Thank you. As Larry Young says, this is one of the more pleasurable events of the year when we get to invite distinguished speakers to share with us some of their experience. And today's speaker is more distinguished than most, if I may say. I don't want to go through year by year his entire life history. Hopefully all of you, when you came in, did get a copy of the program, and there are 2 full pages detailing Professor Giacconi's contributions. I will say 1 or 2 things by way of highlight, however. First of all, the work for which he received the 2002 Nobel Prize in Physics was really involved with the birth of a new science, which is X-ray astronomy. As most people here know, astronomy for centuries was limited to what we could see with our eyes. When the Nobel Prizes started to be awarded early in the 20th century, for almost the entire century, no Nobel Prize ever went to an astronomer, and there are numerous urban legends as to why this is, which I won't go into. But that tradition was happily broken when Martin Ryle and Tony Hewish won the Nobel Prize for work done in radio astronomy, and now we have another Nobel Prize for work done in X-ray astronomy. However, Professor Giacconi, of course, was not satisfied to remain in one narrow region of the spectrum. His work as the first director of the Space Telescope Science Institute, which managed the Hubble Space Telescope, both through thin and through thick, involved visible and ultraviolet. He went on in his work as the director of the European Southern Observatory to work on ground-based visual observation. And now, as president of AUI, he's responsible for managing the National Radio Astronomy Observatory. So he really has spanned the entire spectral range of astronomy. And in fact, their newest project is the Atacama Large Microwave Array, so yet another region of the spectrum with which Professor Giacconi is becoming acquainted and lending his expertise. It's a unique opportunity to have somebody who has really started a field and has turned it into one of the most productive areas of astronomy. And Professor Giacconi, I'd like to ask you to come up and share with the audience your insights into what we've learned about the background of X-ray astronomy.
Do I have? No, it's
Are we
on.
working?
Yeah.
Okay, thank you.
Thank you. Thank you, Jeff. It's nice to be back here, see a lot of familiar faces, old friends. I spent a lot of my career here in Boston and Cambridge, and so it's always a homecoming. What I will try to do today is I will not try to give you a historical, correct, how do I get it lower? I mean, I hear the...
Don't. They'll
Hello?
adjust it for you.
Okay, fine. I mean, I'm hearing myself with echoes and so forth. So what I will try to do today is to take a thing, a problem in X-ray astronomy, and which actually happened to be discovered, the X-ray background happened to be discovered in the very first rocket flights, which revealed the existence of celestial extrasolar X-ray sources, and then try to follow the progress in understanding what this background was till fairly recently, I mean, this year, last year. And that allows me to go through also the technological development which was involved and the progress of the field with respect to sensitivity, angular resolution, and so forth. So by discussing the X-ray background, we touch on a lot of topics. So the first thing is the 1960-62, when we started looking at possibility of doing science in space, and in particular, it had become quite clear by then through the work, for instance, of Herbert Friedman and his group at NRL, who had used captured German V2 rockets to put on instrumentation and study the X-ray emission from the sun, that there was great advantage in working in space, and the ability to look in regions of the spectrum which would not, in which the light would not reach the Earth. So there was a general interest in looking at ultraviolet radiation, gamma ray radiation, and X-ray radiation. I didn't know anything, happily, about all of this until I met with Bruno Rossi, and he suggested, he was chairman at the time of Space Science Board, discussions that occurred there, which included many participants, but he transmitted this information to me, and for some reason or other, that seemed to be a very nice thing for me to do. However, my background was in elementary particle physics, and I detested low statistics experiments. My thesis was, I was up at Plateau Rosard, wonderful place to ski, 3,500 meters, and it took me 2 years to collect 80 protons, in which I was studying interaction of protons with in lead, and I barely was able to confirm Fermi fireball model. I thought, forget it. I mean, I don't want to get into another field which is like that. And that's what you would conclude as soon as you start studying the emission from the sun and you try to put it at the nearest star. That is, we were talking about sensitivities which were 5 orders of magnitude or 6 orders of magnitude below the kind of experiment which had been done up to then. So I actually considered for a while giving up, and then 2 things happened. One is we went through and by we now I mean George Clark, Bruno Rossi, George Clark of MIT, Bruno Rossi and myself, is a brief review, as physicists will do, right? What is the problem? What are the expected fluxes? How do I do a crucial experiment? And what we found out was that what people have been trying to do was not adequate, because the brightest sources we could conceive were in the sky would give us something like 10 to the minus 7, the flux of the sun, 0.1 photon per square centimeter per second. Okay. And so the question was, could you start building detectors that would be sensitive to that kind of radiation? Turned out the answer was yes, but also at the same time, by chance, I mean, since I'd been thinking about focusing my protons there on the cloud chamber, by chance, by reading Flügger, I came up with the idea that, well, I learned that it was possible to have total external reflection from surfaces of X-rays, and the immediate thing, as soon as you know that, and then you have had a mother like I did, who is an expert in projective geometry, you come up with a paraboloid as a concentrator, right, for the X-ray flux. And that was actually done before we started, you know, any real detailed instrument design, because it was important psychologically, because it told us that even if we had to go 6, 7 orders of magnitude, ultimately we could do it. And so it wasn't useless to start, you know, with simple experiments and then a long technological development for the X-ray telescope, and both started essentially at the same time, 1960. There were now this was the payload which was first successful. The payload, this is inside the rocket shroud. So imagine a shroud around it with 3 windows, okay, 1 each, 1, 2, and so forth, and 1 that you don't see. There were counters, and to make it simple in my mind, I think of this AAA changes between this instrument and what had gone before. The change number 1 is the area had increased by a factor of 10, 20, with respect to what had been done before. Then 2, second A, anti-coincidence. It turns out that the background of X-rays is about 1 particle per square centimeter per second. And if you're trying to find sources which are 0.1 photon per square centimeter per second, then obviously if you can eliminate the background due to particles, that will help you by a tremendous amount. And the third A, which had not quite been realized, was the following. If I try to scan the sky with 3 degrees field of view, then my probability, if I launch a rocket, my probability of finding a source anywhere in the sky with this small field of view is about 1%. So in principle, I should fly 100 rockets to find 1 source. I mean, that doesn't... Furthermore, even if I find it, so to speak, meaning if I cross it, then because I only have a small field of view and the rocket is rotating, I will not collect photons. And so in effect, you can show that those instruments would never have been able to detect SCO-X1, the brightest source in the sky. So when we finally flew this instrument, there were 2 characteristics which then introduced the subject that I want to discuss in the rest. One was that we were able to see the first star, so to speak, or stellar system that emitted X-rays. And 2, that it revealed a background, a uniform background, which we could decide was a background due to radiation and not to particles, because we could actually measure the spectrum by having 2 counters. This actually shows the anti-coincidence without the counter. No, this has the counter in it, which had different windows, one thicker than the other. And so you could, roughly speaking, measure the spectrum of the X-ray radiation that went through. So this is all to introduce this picture, which is what we adopted was the anti-coincidence, as I said, the larger area, and a very wide field of view. This field of view is about 120 degrees. So essentially, there was no baffling. There was no attempt to reduce it. And what we found was this very strong source, which I'll move along and not spend too much time on that. That's not my intent. And then a uniform background all over the sky. And we concluded we were able to conclude from this that this was a background which very probably had an extragalactic origin. Okay, now I went through all of the arguments. There was no evidence of increase as you went through the ecliptic or when you went through the Milky Way and so forth. That is the background which remained to be explained for, thank you. Yeah, I didn't know. Right, okay. That was the background that remained to explain and took about 40 years to explain. Immediately upon finding this, a contribution to cosmology was given, because, which was interesting and negative, so to speak. This background, big as it was, and it was very big because, I mean, there is no trace of the cosmic ray component here, was absolutely much smaller than what one would have computed in the hot universe model of the continuous creation theory. So Hoyle immediately realized this, and I mean, one of the things which is fantastic here is that just because he hadn't thought about X-rays, he hadn't predicted it. Otherwise, he would have predicted that the sky was going to be awash with X-rays. But it's interesting that just a negative statement essentially killed that particular theory. The other question, remember historically, that this is the time of finding the 3-degree background radiation. So then there was the measurement of the gamma ray background from the galactic center. And somehow the idea that the background carried information of cosmological significance was around, let's say. So in effect, in 1963, when we had this data, we tried to think about what the background was all about. Burbage was the first to suggest that this background could be due not to a diffused emission, but the combined radiation from very distant galaxies, in which, since we didn't have any angular resolution, and the flux would all be confused together. And so it dictated the design of the X-ray telescope we ultimately wanted. I'm trying to interweave the fact that finding, interpretation of finding, and design of the next experiment are very much a function of what you think of that you're doing. So what I thought I was doing in '63, I proposed a 1.2 meter X-ray telescope, which had the virtue that it could image the X-ray background with the, if you was uniformly distributed with an angular resolution of 1 arc minute, so that we would decide whether it was done with individual sources or not. Okay, so this was the first step. Now, we didn't do much more than this. There wasn't any major change to this until in 1970, we flew a simple X-ray satellite, which, if you wish, is just a bigger counter, one on each side of the spacecraft. The field of view is the important thing. Here is 1/2 of the square degree by 5 square degree, then a 5 by 5 field. This satellite was launched in Kenya, and since it was launched on Freedom Day, Uhuru was called Uhuru. Also because it was so much better than the NASA SAS A, B, C, D, whatever. Uhuru, that is what we really felt. So what is the purpose of the satellite is to do a scan of the entire sky. As the plane of as days go by, the plane of the scan changes, so that you have intersection, you can find the position of sources. And this was done over 2 years or 4 years. Now, here is one scan, this is the SCO-X1, the first star that we had seen and that prevails on the whole sky. This is in galactic coordinate. Here you see now that scale expanded, and you see how many sources we see and so forth. What I want you to do is to ignore all the sources for a moment, and here's the background. It's still there. Okay? And it's in fact the largest background, the largest contribution of the background to the detection of sources. Now, the result, I want to introduce two concepts which then allow me to go on. This is the result of the catalog from the All Sky search, and it's in galactic coordinate. This is the Milky Way, okay? And most of the sources that you see here, which are represented by dots of increasing size depending on their intensity, this is SCO-X1, the brightest one, okay, are galactic. And most of the other ones, or almost all, are extragalactic, okay? They are diffused around. Two fundamental findings of this satellite were, one, the discovery of binary X-ray system, which involved the, sorry, slowly, I inverted the order. This is, the first one was the discovery of hot intergalactic gas. What is this gas? Here is a photograph. This is taken much later, not at Uhuru. This is a ROSAT picture. The X-ray, and what is underneath is I think it's a La Silla picture or something. Here you see galaxies. There are thousands in this cluster. And here you see the distribution of X-rays, which are emitted not concentrated on each galaxy, but in the space pervading the galaxy. Now that sounds, interesting. However, the most salient point is that 10 times more mass is in this gas, a very high temperature, which cannot be seen in visible light, than is contained in all of the galaxies and stars represented in this picture. Okay, so this was finding a new state of matter in which very high temperature gas was emitting X-rays by thermal Bremsstrahlung. And as we go along, you will see why I wanted to mention this. The next thing, and this I won't go through this. The next thing was the discovery of this binary system containing a neutron star or a black hole. And the reason why I'm bringing this up, and this was done in particular was SENEX 3, was that we discovered binary system, a collapsed star, a normal star. Gas would fall from the normal star onto the collapsed star, and the collapsed star, was emitting pulsations. Now, the question that arose was, are these pulsations emitted at the expense of the rotational energy of the compact star, as is the case for pulsars? And the answer is no. In fact, this X-ray source is not slowing down in its rate of rotation, it's acquiring energy. And it's acquiring energy because of the infall of gas onto its surface. And this mechanism, which is shown here, if you wish, in a diagrammatical way, this is gravitational equipotentials. Gas from the normal star falls in the deep potential well of a neutron star, for instance, and acquires more energy per proton that you can obtain by nuclear fusion. So this is a very powerful energy mechanism, and it's now been extended, and in Uhuru it was, as a result of Uhuru stuff, these are not, this was one of the sources which is periodic, which I mentioned now. Other sources show nothing, and then there are very erratic sources. And by bringing to the attention of the astronomical community this unusual behavior, then very good positions were obtained, some from the MIT group, some from Uhuru itself, MIT group using rockets. And then an optical identification was made by Webster and Merlin. He determined that the mass was 10 solar masses, 6 solar masses. There are very rapid variations which involve the whole star, therefore the object, and they're very rapid because these are, at the level of milliseconds. Therefore, the object must be very small, and it's very massive, and it had been shown by Rhodes and Ruffini that no neutron star could have a mass greater than 3 solar masses, and therefore this was by definition a black hole. And what it means is we simply don't know of any physical law that prevents this star from indefinitely collapsing. Now, the point that I am trying to make here is that, without going into all of this, that there was a new source of energy due to gravitational infall, which is very efficient, and a model for what is happening actually in the nucleus of active galaxies and quasars, which explains why the tremendous amount of energy which is emitted by this object. These two facts, that is the idea that very energetic emission in X-rays comes from the nuclei of active galactic nuclei and is powered by gravitational infall, gives you one potential explanation of the X-ray background. The possibility that hot gas diffused throughout the universe it gives you another potential interpretation. And the difference between the two is that one would be a diffuse continuous emission, and the other one would be a point source emission. Okay, so there were some. Now, again, coming back to Uhuru, there was, here is the background. As you see, it's dominating. I mean, here is the cosmic rays, and this is this very strong. This is very different than what you see in the visible light sky, right? It's not like extragalactic component of the visible light sky dominates the sky. I mean, that would be that it's light all the time, so to speak, right? But it isn't. But in X-ray it is so. Then there was a finding which, you know, I thought was very suggestive. If you take the sources which are at low galactic latitude, and you plot how many of them as you go weaker and weaker, fainter and fainter, you find that at a certain point, you stop increasing the number because you're running out of galaxy. If, on the other hand, you do this for extragalactic sources, their number keeps increasing as you go to fainter and fainter magnitude, as if the cosmic expansion were balanced by evolutionary increases. Now, this actually was done by, I see, by Matilsky, who was, was a real 60 kid, I mean, motorcycle type. But that was a very profound finding. Okay, so here one could be led to the conclusion then, okay, so if the extragalactic sources keep going up and up and up, then we have the exponential background, right? And in fact, this was suggested actually by Bolcher and Sethi. If all sources extragalactic were emitted like a quasar, then we would explain the background. And here, again, I'll jump this away. Now, the other question was, well, what was the spectrum of emission of the background? And that was, it looked somewhat simple. This is a composition by Gorenstein, I believe, of the emission from different sources. And it was clear that you could explain it either with a thermal Bremsstrahlung spectrum, which is shown here, or by two power law spectra. And this was about what we knew. Now, the next piece of important information, or that seemed extremely important at the time, was this one. That is, this is now 1978. Uhuru was 1970, this is 1978. Here one flies. It's a very large counter. And it finds the spectrum of the background, and here are different fits. And as you see, it fits perfectly a thermal Bremsstrahlung spectrum at 40 kilowatts. And this became ingrained in everybody's mind, and therefore, there was the conclusion, well, this had to be thermal Bremsstrahlung from a hot gas filling the whole universe. Now, never mind that this actually required more gas than the total mass of the universe. I mean, this was, and that if it existed, you would have to explain how, after cooling it at 3 degrees, which is what we see in the microwave background, then you were able to reheat it at 40 kilowatts, okay, which were a little problems. But never mind. So this was, okay. And I think that beyond that, I stopped going with the known imaging experiments, not using the telescope, because there was no more progress that was possible. And here I just wanted to show you why X-ray telescopes can be important for X-ray astronomy. Here is the absorption in the atmosphere, okay? So if you go up, you see more, right? Because this is absorption at, I think, 1/2 here. 100, 1/10, 1/2, and so forth. Here is a spectrum of a potential X-ray source. And I think it was Giacconi who pointed out that in normal high-energy sources, the number of photons decreases as the energy goes up. It's an empirical law, if you wish, but it works. And here is the limit in which you can reflect with total external reflection X-ray efficiently at about 1 kilovolt or up to 10 kilovolt. And here is the window of detectors that we can build. I mean, it's difficult to have detectors which go to softer and softer wavelength. So in this particular, the reason why X-ray telescopes are useful is because they work here and maximize in a region in which you have the maximum statistical number of photons coming in from a source. Okay? Now, why wasn't this clear? Because it took a long technical development to come up with telescopes, and okay. This was a 1961, statement of what a telescope would look like. You need a double reflection to make an image. This had been done by Folter in 1952 or something, because he wanted to build the microscopes. He ultimately never could build them because they were so small he couldn't actually do this. But for telescope, where you are talking about large surfaces, then you could polish these inside surfaces to very high accuracy. And the trick was that you have to have extremely good surface polish, much better than what you normally need for optical telescope, down to 3-4 angstrom of surface roughness. This was hard. It took many years. Little telescopes, okay, replica telescopes made of mandrels. This was the first serious telescope, I think, for solar research, and which already had some of the features that would be necessary for stellar research, where you need more area, so you make many surfaces one inside the other. This particular telescope flew on Skylab, the mini space station, 1973, and took a picture of the sun. And I use this to show you, yes, the technical progress, but also the fact that it's amazing that just this picture tells you the very important role of magnetic fields in the containment of the hot gas and in the production of flares. Okay? So that revolutionized solar X-ray astronomy and actually the study of the corona. This was Vaiana and Van Speebroek. Now here's the first application or attempt to use an X-ray telescope for stellar astronomy. Surfaces had to be much better polished, more area. Here was the interest of doing many things. 4 groups were involved, Goddard, MIT, American Science and Engineering, Harvard, and Columbia. And spectrometers were put here, and you could turn for this Lazy Susan and have a solid-state spectrometer, imaging proportional counters, focal plane crystal spectrometer, etc. I will just focus, because, you know, as a monomaniac, I was still trying to find the source of the background. So what I did was to choose a region of the sky where no X-ray source was known, and we pointed to this for 10 days, 1 million seconds. And this is mostly background. There are 3 sources here, 1, 2, 3. And then to give you an idea of what we are dealing with, the faintest sources that we were seeing was something like 10, 11 counts. So it was 1 count, 1 photon a day that we would collect. That is also the limit at which we are going with Chandra, exactly 1 photon per day, but now to much fainter sources, okay? But it's, X-ray astronomy is not easy, is what I'm trying to say. Here was the same field. Unfortunately, I should reverse it, but those 3 objects are identified now with stellar-looking object. 2 of those are quasars. 1 of them is a star, a normal star. So one can draw the conclusion, and here I'm going to the very early Uhuru data, and then you see this where the galactic stuff, extragalactic stuff, SCOEX-1, and the deep survey goes down by 2 or 3 orders of magnitude in sensitivity, and yet this trend of the increase in sources as you go fainter and fainter continues. Now, the problem with all of this is that these measurements are made in a specific region of the spectrum, 1 to 3 kilovolt. And so there succeeded a long debate because of what was the spectral content of this radiation, and whether this was just a fluke where we were measuring a background that really was on the background that one would like to understand. Now that was very difficult to deal with because at the time we just couldn't go to higher energy. The mirrors were not good enough and so on. Now, however, there were some interesting points, and this was one of the attempts we made to put some rationality in this research. What had been found was that spectra of the claim for the proponents of a discrete source origin for the background, basically we're saying that active galactic nuclei, C4 galaxy, quasars, C4-2, etc., would make up the background. For the few sources for which the spectrum had been measured, spectra indexes which were very steep, that is, much more low energy than high energy stuff, were found. And it was very difficult to explain, therefore, how the background that looked much harder than what each individual sources did could be generated without assuming evolution or change in the spectrum. So what we tried to show was a kind of reasoning ab absurdum, which I think had to come from a Jesuit education or something, I don't know, which was like this. If you assume that 50% of the sources are due, or 70%, depending on what you like to do, are due to these individual sources that we have measured, whose spectrum we have measured, then the spectrum that is left has to be very hard, right? Because we are taking a spectrum which is soft, spectrum that is left is very hard. Now, could this spectrum be a Terma-Bremsstrahlung spectrum? The answer is no. There is no way you can reproduce the slope of the spectrum with Terma-Bremsstrahlung from an optically thin gas. So in order to explain by diffuse emission what this the residual background is due to, you have to imagine that you have gas, yes, but that you have to have absorption in the gas such that the low energy are suppressed and you allow high energy to come through. Now, in order to do that, you need balls of gas of certain optical depth. And you can do it one or two ways. Either you have enormous balls of gas with very low density, or small balls of gas with high density. So what we said, well, how do we decide between this? Well, we decided on two grounds. One, that we wanted to have enough optical depth to get the absorption effects we wanted. And second, that the total number, the total mass contained in all of these balls of gas, which had to be millions because we were seeing the background to be very homogeneous, could not exceed the mass of the universe, which seemed a reasonable constraint. Well, if you put that constraint, that immediately collapses, says that all of these balls of gas that you're talking about, that should fill the universe uniformly, have to collapse down to 100 kiloparsecs. So that means they would be the size of our galaxy, and therefore it shows ab absurdum that these postulated sources of the continuous background actually have to be point sources. Now this was a paper, I think one of the better papers I ever, but actually it wasn't understood at all. My referee said, well, why don't you talk about the physical characteristic of these objects you're describing? And I tried to explain, but anyway, interesting. So in any case, I claimed that by 1987, the problem of the background was solved. That is, we knew it had to be due to discrete sources. However, we had to prove it, and we had to show that the spectrum, etc. So now, and I won't, there was a flight of a German satellite. Joachim Trumper built ROSAT. We went with deep surveys. I was fortunate enough to be involved. I mean, this was the group, and we found 70 to 80% now the background. Again, remember, at low energy. The spectrum of the sources, et cetera, et cetera, et cetera. And still, And the composition, what were the sources? Each one identified 39 AGN, 1 galaxy, 3 galaxy group, 3 stars, 4 unidentified objects. Still, there was this problem of the spectrum. And so finally, it only got solved with the advent of AXA, which only happened to be launched in the year 2000. Now, AXA has the angular resolution. This is not that I want to discuss pulsar emissions, but it has the angular resolution to give you this direct picture. This is no artist's conception. This is the picture of the Crab Nebula showing the shock waves and so forth. There is a movie of it, but I'm technically challenged in showing it to you. And I just wanted you to understand the power of the instrument. This is as good a picture as you can take with Hubble, essentially, of the Crab Nebula in visible light. So naturally, I didn't take that picture. My time, I devoted for looking at the region of the sky where no source was known before, and I asked for a millisecond. I got a millisecond. And here now is the field of view of the CCD, which looked at this region. And we are finding a source density which is really enormous with respect to what we were finding before, because there is something like 300 sources containing 1/10 of a square degree. So this is not as high as the source density we see in Hubble, because we are looking at galaxy. But basically, 90% of the sources are black holes, emitting energy by the mechanism which I was explaining to you before, infall from an accretion disk onto a supermassive black hole. And the rest are interesting in their own right. This is an attempt to show in a color. I won't go through this. Here is a summary of where we are now in sensitivity. So this was my chance to show you that we went from 10 to the minus 7 to 10 to the minus 17, or several times 10 to the minus 17. And this was in 40 years, which is not bad. It's equivalent to going from the naked eye to Keck or VLT. So it's okay. The field is moved. Now here is the contribution of those sources. Now you can sum all of those sources, okay? Sum all those sources, and this is big arrows, and this is the determination of the background. So you see that one of the problems saying how much of the background is due to individual sources, we don't know. Really, we don't have very good measurement of the background. And, but, okay, there could be some diffuse background still there, and that would be very interesting if one could actually prove that it exists. Now, the next thing which was interesting is, remember, we are having very few photons. So when we talk about spectra, we have to sum. So this is the summed spectrum of all of the sources with something of the instrument signature, and then a fit to the background spectrum. And as you see, it essentially reproduces the background spectrum completely. Now, this is a conundrum, right? Because when we measure a few sources, they seem to be different. Now we're measuring them all, and they fit. So something is happening. And here is the different increases by the number of sources, and we can go now to 10 kilovolt, okay, which is kind of nice, so that we don't have this problem that we don't see the high energy sources. And you see here that at the low energy, the number count of sources seems to be turning over here and here. And at the high energy, 5 to 10 kilovolt, it seems to keep going, and is going faster than in the other spectral region. Here is another attempt to show, to show what is happening here. So, and each one is a source. We don't have enough to measure the spectrum precisely, so we do take what we call a hardness ratio, hard versus soft ratio. And what you are seeing is that you go fainter and fainter here, the hardness ratio increases. So what it is that the sources are changing their spectrum, or you're picking up different sources than what you were picking up when you were looking at when you were looking at bright ones. And here, for instance, the same trend, the spectral slope, which is given by this gamma, is going down as you go to lower and lower fluxes, so the spectrum is becoming harder. And now the next step, okay? What are the sources? So this is the overimposed Chandra isointensity contours in X-rays on the Hubble ACS large camera deep survey of the same field. And what you see is 2 points. One is that it's really important to have the very high angular resolution. Look at this, for instance, I mean, right? The very high angular resolution of both Chandra and of Hubble to identify sources. Now, once you have identified the sources, then you can go to spectral measurements. And there, it's important to have even larger telescopes than Hubble. So much of what I'm going to discuss now has been done with Hubble, Chandra, and the VLT, which is the European Southern Observatory 4 meters telescope. It's the largest aggregation of telescopes in the world. So what do we find? Okay, the first thing we find is that, okay, this was simply said the hardness ratio seems to go, has a dependence on the brightness, the intrinsic brightness of the source. If you measure redshift, you can get intrinsic brightness. These objects, which are star, are quasars type 2, which had, of which one had been known before. So they are objects in which presumably you're looking at them face in, I mean, without the absorbing effect of the gas of their own galaxy, intrinsic absorption of the galaxy. These are the these softer sources because you're seeing them like this. These are the harder sources because you see them through the gas of the galaxy. And they tend to be somewhat of lower emissivity, intrinsic emissivity. Here are sources which are very, very soft, -1, and they're galaxies. Okay? So what we are seeing here is C41, C42 type active galactic nucleus, but they are all active galactic nuclei. And here we are seeing possibly some clusters, and here we are seeing galaxies. Okay, let's go on one more minute. The ratio between visible light here in magnitudes, R magnitudes, and X-rays is more or less what had been found before. These lines, 1, 0.1, were found even with ROSA. Here are the galaxies again, okay? Here are those objects that I was telling you that are soft. And here are the hard ones. And here are objects which are seen in X-rays, even very bright X-rays, but are not seen in visible light down to 28th magnitude. And I can assure you that observing objects at 28th magnitude becomes challenging, not only for ground-based telescope, but for Hubble. We have been able to basically, the reason why you see the sources identified up to here is because it really is an 8-meter telescope or 10-meter telescope to measure the spectrum. And you can try morphological identification, et cetera, et cetera, et cetera. But basically what I'm trying to say is that the X-rays have allowed us to look at objects whose nature we do not yet know. We need a bigger visible light telescope or possibly ALMA in the millimeter wave to actually identify these objects. The next thing was, okay, so what I'm trying to say, the closing remarks of this talk, over long I'm sure, is the following, that the problem of the origin of the spectrum has gone away. Obviously, it was a known problem. It was a fiction of the theoreticians. I mean, we just needed angular resolution and powerful instruments to solve. But what has happened here is that now, actually, I want to go back here once. Now, what we are engaged in, here we go, is we have broken through this fog. We are seeing the individual objects, and now we study them. So the first thing we did the reason why I went back, I wanted to pick up this group, which is galaxies. And the first thing we were able to do is to measure the rate of star formation in X-rays in galaxies at very large distances from us. And it's an interesting problem. It was compared to the known or measured star formation rates in other wavelengths. It turns out it agrees, but this is the star formation rates of binaries, it turns out. Okay? Here, another aspect of the results is that when you distribute these sources in redshift bins, you see these clumps, which have been seen in visible light. These are clumps which are observed in X-rays, which means these are active galactic nuclei. They are not clumps of galaxy, they're clumps of active galaxy, or black holes, or call it super black holes. And finally, the study of clusters and the emission of clusters, the largest assembly of matter, discrete matter in the universe. This is a picture taken in one of these very deep fields of a very faint cluster. And this was done not only by us, but also by the people, Bauer and Niels Brandt and so forth, who have been doing the same. This is our work and this is their work. But basically we have extended the region in which we see clusters by several orders of magnitude. Again, a little dig to the theoreticians, which have been a pest in my life. We had a wonderful experiment which we had proposed, which was turned down not only by NASA, but by ESA and by the Italian Space Agency. On the ground, that no cluster existed at this early epoch in the universe. I mean, now I could kill him. Okay, but that's their job. Now, finally, something that we have found out just a couple of months ago was, okay, now we have all of the sources. Do they vary? If they are accretion disk providing matter on a supermassive black hole, then as this amount of matter changes in time, then you should see changes in the emission of the X-rays. And what we find is we find variability. Now, again, this was done in a very stupid way. That is, we plotted out the actual intensity that we would measure in the different observation times. And we found out that there was a difference from one observation time to the other. Now, why two other groups had tried to do that and didn't succeed? Because they were applying overall algorithms that would measure this and that and so forth. Very sophisticated, in fact, software, but not as simple-minded and revealing as this very simple kind of approach. So I'm saying sometimes, you're too smart for your own good. Here we did find sources which are variable. And here the plot, I'm showing you very little, but the plot has to do with hardness ratio. So it says that the ones which are most variable are the ones which have the lowest hardness ratio, which has to do with type 1 and type 2. That is, again, you're not seeing absorption in the line of sight because in the C4 types 2, you have to have scattering, and therefore you have dilation of time. And this is the ratio of what happens, and this is very strong. And again, the next slide shows this done now as a function of redshift, variable and non-variable. And it shows that the most variable one are the one in which the intrinsic absorption is lowest, which means that the hardness ratio is lowest. Okay? So this is just a repetition of that set. So to conclude, I think that I can say, well, we have solved the problem of the background, I think. There may be an experiment to find out, is there really a new, some diffuser component? Second, we find many of these type of sources, clusters, AGNs, galaxies, and then 10% unidentified, which I am we are convinced that it may be something new that we haven't understood yet, but we will need more powerful optical and radio telescope and so forth to see it. I hope to see it within my lifetime. I mean, I've been waiting 40 years. It seems reasonable. Okay, very high source density. The possibility to study, 1/3 of the sources are in sheets, just like it happens on galaxy distribution. And basically what the background has turned to is this, is the deep study of evolution of galaxies, of AGNs, and large structure. Well, I'll stop here. Thank you. Not bad.
We'll have a little time for questions. First of all, I want to mention kind of an underlying theme in the series of lectures we give in this Modern Space Science and Engineering seminar series, is that there are fascinating scientific questions which can only be answered with recourse to space observations. And in doing this, we have to solve a lot of very sophisticated and fascinating engineering challenges. And Riccardo, I think your talk has illustrated this perfectly. There's fascinating scientific questions, and you've also taken us on a tour of the history of the development of X-ray technology. If I could ask the first question, what would you like to see as the next technological development, maybe to take us the next step?
Well, I would like to see, we need a little, another factor of maybe 100 to make a real difference. So there have been...
You're always thinking big, I love it.
Well, I mean, it's, it's 3 magnitudes, let's not... Also, I think that it's important that we maintain this, the thing that makes me happiest is that in this last experiment I was able to use Chandra, which I proposed together with Tannenbaum in 1976, and then Hubble that I was involved in directing, and then VLT, which I was involved in building. So it's, to me, they are all part of the arsenal, okay? It's very important that we keep this capability in balance. I personally feel that the millimeter wave interferometry array, which will come in being in 2007, 2008, the first manifestation, is going to be a very powerful tool here to carry out this research. I think it's important that we go on in X-rays because every time we turn around, we get new discoveries. I mean, we absolutely did not know that there was this kind of spectral evolution in AGNs. We still, it's not clear, no model we had of the X-ray background actually explained the data that we have seen. So that, and so we need more area. Unfortunately, that has to be coupled to high angular resolution because, you already saw, for instance, there is the Chandra spacecraft is more sensitive than the XMM spacecraft of the Europeans, even though XMM is larger because XMM gets confusion limited. So if you're looking to a nearby source where you don't care about confusion limit, then you can get a lot of photons, you measure spectrum more. But if you're really looking to very distant sources, then you really need angular resolution to know what you're doing. So angular resolution, spectral resolution, and area, right? That's what we need.
Some questions from the audience. And I'll mention that we'll have a short question period, and then we do have some refreshments, and we invite you all to stay, enjoy the refreshments, talk informally with Professor Giacconi and with one another. And I'll remind the students again who are enrolled in the seminar at 4:30 when Professor Giacconi will have to leave us. Please come up to the front and we'll continue with our work. So, some questions?
Yeah.
Riccardo, if you're trying to look at a background, of course, it's like the radio problem in the background here. You can generate it in your equipment. You can generate it in a phony way from cosmic rays.
Yeah.
And both of those problems were overcome. Were they relatively straightforward? Did they require clever engineering? Or what?
Well, the cosmic ray is, we really don't have very effective anti-coincidence against cosmic ray right now. But the cells of the CCDs are so small, they're 20 by 20 microns, right, that the rate of cosmic ray is very low. And also the EDX, which you see, is different. I mean, the position of energy comes in a slightly different way. So you can try pole shape discrimination, which is being used, and also seeing if you have more than one pixel involved, and so. But it's rough. I mean, and now we still are signal limited, which is an important point. So that as we go 100 times, and we have the adequate resolution, we are going to go to 100 times in sensitivity. That's a big advantage of a telescope with respect to simply a counter, right? Because a counter, you just increase the sensitivity by the square root of the area, but you know, to have the sensitivity of Chandra would require a mile by a mile Uhuru, I mean, right? So, and I don't think you could have done it. So that was a problem. The other one you mentioned was?
Generated inside.
Well, that again, we used pole shape discrimination on Uhuru. There were two counters side by side, so you, okay. I mean, yes, but not, it wasn't a physics problem. I mean, it's not like, you know, trying to invent an accelerator. I mean, it was okay, but, right? Yes?
Hubble Space Telescope is not going to be serviced in the future. That's what's being mentioned in the news. How is that going to affect research in X-ray background or, for that matter, space research?
Well, if I had my radar, I would, and I think I expressed the view of much of the community involved, that it would be nice that if we could be assured of continued operation of Space Telescope. At the moment, we have absolutely nothing with that kind of refinement, for instance, to look at morphology of some of these objects, which we are doing now, or to make the statement that there is no object corresponding to this one. You have to have extreme precision of position and sensitivity, okay? On the other hand, you know the well-known discussion. It is a general problem with NASA that they start a discipline, but they don't support it in a steady state. They find it very difficult to support a steady state operation of anything. So, for instance, this problem will occur with Chandra and X-ray astronomy, unless we do something about it. As soon as Chandra case cannot be serviced because it's too far, elliptical orbit. So as soon as that dies, then my estimate is it takes 20 years. I mean, 10 to sell and 10 to build, and right? It takes 20 years. And you know, so it's going to be tough. And I think that the only thing that sustains us really is that altogether astronomy has had tremendous progress, right? And if you become frequency agile, so to speak, you know, to me it has happened. I've gone from high energy right to low energy as I became older and older. So now I'm in radio. I mean, I can't. But anyway, the problem is what should be driving you is the problem that you wish to solve, and you can solve it in a variety of ways. And you have to be reasonably agile in the sense that if you wish to use observational materials, you've got to use the observational material that either you can produce by building an instrument that is within your means, or you get it from the virtual National Observatory, from the data bank of Hubble. I mean, half the research of Hubble right now is done on archival research, not direct observation. And this is, unfortunately, a prevalent trend. Unfortunately, because it creates a generation of astronomers who never had to build anything. They just have to analyze data. And the question is, who's going to build the next? And it's a real issue about training and passing on a culture. But that's as it is. So, I don't know. I answer you with too long. I mean, now. Yes? No? Okay? Are we done? Refreshment?
Well, just before we break for the refreshments, we want to thank you once again for taking the time to come and talk to us. We do have a certificate of appreciation, maybe not quite as significant hanging on your wall as your Nobel Prize, but
I don't hang anything on the wall. I mean,
it's
nothing.
heartfelt. We appreciate it.
Thank you. Thank you. It's a pleasure.